In this journal club, I would like to briefly talk about two recent experiments which shows that there is no heat flow in the ground state of a charge-neutral mother layer and the bilayer graphene in a magnetic field which is perpendicular to mother layer or bilayer graphene. Here I put the main references if you are interested. Now the question is that why they want to measure the heat transport of these systems. After this journal club, you should be able to understand the reason why they measure the heat transport of those materials in an external magnetic field. Also, you should be able to list the four potential candidates for the ground state of mother layer or bilayer graphene in an external magnetic field. Lastly, you should be able to briefly describe two recent experiments which show no heat transport in the charge-neutral mother layer and the bilayer graphene. Here we show the Brillouin zone of the mother layer graphene. This is the K point or valley and the K prime valley. Once we put the material inside a magnetic field which is perpendicular to the graphene plane, in a single particle picture, we can use the Landau levels to describe its energy. The energy is controlled by the Dirac velocity and the magnetic length, which can be tuned by the magnetic field strength. In the charge-neutral graphene, we notice that there are four degenerate states: K spin up, K spin down, K prime spin up, and K prime spin down. However, each carbon atom in the unicell provides one electron, and we have two atoms in the unicell, so we have the half-filling scenario. Therefore, in principle, this system is electrically conductive. However, experiments shows that suspended mother layer graphene with half-filling is an insulating state. Other experiments where graphene with different substrates and bilayer with and without substrates also show an insulating phase as the half-filling. Understand the nature of the insulating phase is, however, a challenge. Okay, to understand the nature of the insulating phase, we could start with theory, an Hamiltonian that contains the periodic potential from the nuclei and the external magnetic field in the kinetic energy and the Zeeman term. We also consider electron-electron interaction and electron-phonon interactions with electrons coupled to these in-plane phonon modes. In this paper, the author constructed an associated Lagrangian for the charge-neutral graphene with the kinetic energy and the potential energy in terms of an ordered parameter, which describes how electrons are distributed in valleys or so-called isospins and the spin direction. The potential energy term consists of three terms. Here, the most important one is the so-called isospin and isotropic energy. We also consider Zeeman energy term here. Given the isospin and isotropic energy, which can be specified by U perpendicular, which is described the in-plane situation, and UZ describe the quantity perpendicular to the plane, and the Zeeman energy specified by epsilon Z. We can find the ground state by minimizing this energy term to find the order parameter. This approach can be also applied to bilayer graphene. If you are interested, you can look into this paper. Next, let's see what ground state we can obtain from this approach. Given different values for the isospin and isotropic energy and Zeeman term, four potential ground states can be obtained. The first one is the spin polarized ferromagnetic phase with all the spins pointing toward the same direction. The second one is the canted antiferromagnetic phase with the spin configuration schematically shown in this figure. The third one is the calculate distortion phase with the mixing between different values. The last one is the charge density wave phase or fully sublattice polarized phase with two opposite spins located at the same sublattice. The spin polarized phase is charge conductive, while the others are charge insulating. These three phases will be the insulating phase. That's what's observed in the half-filling scenario that you saw earlier in experiments. However, the question is that which insulating phase is for the half-filling case. To distinguish this, we could probably look at another material property, thermal conductivity. The candid antiferromagnetic phase and the calculate phase are thermally conductive, while the charge density wave is thermally insulating. If you are interested, you can probably look into this paper. In addition to this graphene, monolayer graphene, similar ground state phases are predicted for bilayer graphene. If you are interested, please look into this paper. Okay, so in the next two slides, we are going to look at the two recent experiments which shows that the insulating phase of the neutral charge neutral monolayer and the bilayer graphene might be the charge density wave phase with no heat transport. To find out the nature of the insulating phase, a recent experiment for measuring thermal transport of monolayer graphene was carried out. In these experiments, the authors using two different configurations for thermal devices. The first one is a two-terminal device with two floating metals between which are the monolayer graphene in the half-filling scenario, μc equal to 0. Outside the floating metals are the graphene with filling numbers of mu equal to 2, which can conduct heat via H states. Here shows the results. When one metal is heated up by an external current, its temperature is shown in red, and the black line is the simulated result using the H heat transport model. Interestingly, the temperature of the other metal is not affected. Similarly, if you heat up another metal and measure the temperature of the other one, the results are the same. This result indicates the half-filling graphene is thermally insulating. The second scenario configuration is a carbonyl heat transport device with a floating metal at the middle. On top of the metal is a graphene used to heat up the metal, while at the bottom is the graphene that we are interested in. The authors measure the temperature of this floating metal using the top and the bottom graphene. The measured temperature difference between these two graphene is denoted as delta Ts. The filling of the bottom layer graphene can be controlled by a local gate. At a half filling, μc equal to 0, the data are shown in magenta. The others also choose another filling number, μc equal to 2, for the bottom layer, which is believed not to support thermal transport, and the results are shown in black line. Both results agree with each other, indicating that the half-filling phase is thermally insulating. Next, we look at another recent experiment on measuring the heat transport of bilayer graphene as the half-filling scenario. The experimental setup is shown here. We have two regions. In the middle, we have the floating metal, which serves as the heat source. The floating metal can be heated up via the edge channel of the bilayer graphene at the left-hand side. The region at the right-hand side is composed of two small regions. One, the upper one, can be controlled by a local gate to realize different feeding numbers. We can tune the upper one to have feeding mu equal to 0 or another feeding mu equal to 4. If the gapless collective excitation exists for mu equal to 0 state, extra heat should flow from the half-floating metal to the cold ground in addition to the electronic heat flow through these edge channels. Using this setup, the authors can measure the temperature of the floating metal using the graphene. The temperature Tm of the metal is proportional to the thermal noise S1. The rate data refers to 4-4, which means the feeding values for the left-hand side and the right-hand side respectively. The black data refer to 2-0, with the upper region of the right-hand side being half filling. We can see that the measured temperatures in both cases do not differ too much. From the temperature Tm, we can estimate the heat flow for both cases. The results are shown in red and black. The heat flow curve follows the edge electronic heat flow model shown in dashed line, indicating that half-filling case does not contribute any additional heat conductive channel. Okay, so we have seen the results of the two experiments indicates the insulating phase might be the charge density wave phase, which does not support heat transport. Now you could try to test your understanding by answering these questions. Okay, so that's all. Thank you for your listening.